In this lecture, we are going to discuss gauges in electrodynamics, and we're going to go over two well-known gauges. We're going to discuss the Coulomb gauge and the Lorentz gauge. So in the previous lecture, I described mathematically what a gauge is, and now we're just going to go through some examples and show how these two particular gauges clean up our second-order differential equation for the potentials in a very nice way. So let's start with the Coulomb gauge. So for the Coulomb gauge, we choose as our gauge that the divergence of A goes to 0. Okay, so that means if I look at Maxwell's first equation, where E is this equation here, that when I take the divergence of E, I get minus the Laplacian of V, and minus the divergence of A, which is equal to rho over epsilon naught. So since I said it just at the very beginning, the divergence of A is 0, this goes away, and what I'm left with is the second derivative with respect to space of V is equal to minus rho over epsilon naught. Okay. It's called the Coulomb gauge because we've seen this before. This is an example right out of electrostatics, and you can solve this where you get basically Coulomb's law. So basically you get an integration over the volume of the charge density of that. So the interesting thing about the Coulomb gauge is that that changes to the charge density will be known instantaneously throughout the universe. So any change here will be a change in that function rho is going to be seen here and in the next galaxy over. And so the problem is that violates special relativity. So we're kind of dancing around the concept of the fact that this gauge is going to be a good choice to solve the problem, except for the fact that it violates special relativity. The good news is we haven't really worried about special relativity yet, so let's just kind of ignore that. Yeah, so we'll ignore that for the time being. We can kind of wave our hands and say, well, I don't have to worry about violating special relativity because I'm not actually going to measure the potential V. Instead, I'm going to measure E, which is the change of potentials. And so in the end, that's going to solve the problem. Okay, so now if I put this into my second-order differential equation, what I will get is Laplacian of A minus mu 0 epsilon naught, the second derivative of A with respect to time, and that's now going to be equal to minus mu 0 J, the current, plus mu 0 epsilon naught, the gradient of the time derivative of V, like so. So essentially what we did was we chose the gauge where the divergence of A goes to 0. That eliminates the divergence of A part of this equation, and we're left with basically a second-order differential equation with A dependence on this side, and over here, what you get is J and V dependence. So we kind of can do this nice separation where we separated the A's from everything else. So now, you can, and a lot of times V is easier to solve for than A. V is a scalar, A is a vector. So V can often be, like I said, easier to solve. So that reduces the problem a little bit, where now all you have to do is solve a second-order differential equation on the left with respect to some stuff on the right. And if you can have a good example, if you choose a good example for V such that it cleans up the problem, then, it's not that difficult to solve. The next gauge, which we can take a look at, is the Lorentz gauge. Okay, so our choice of gauge here is to have the divergence of A equal to minus mu 0 epsilon naught, the time derivative of V. So that's pretty good, because in the end what that does is it eliminates everything that has to do with the gradient, and we're left with only a function of A. So our second order differential equation simplifies to this right here. And that's really nice. So we've eliminated the electric potential altogether. It cancels out in that gradient term, and we're left with just a second order differential equation with respect with the function A in it. And then if we have a good choice of current J, then then we can solve this problem. So in the end, I just want to emphasize that there is no V dependence at all in the solution. We've eliminated V with a choice of gauge. So when that's the case, then if we go back and take a look at Gauss's law, or Maxwell's first equation, what we had was the Laplacian of V. Now we can substitute out the divergence of A with respect to V, and we get the time derivative of minus mu 0 epsilon naught, the time derivative of V, and that's equal to minus the charge density over epsilon naught. Now we have a second order differential equation that only depends on V. So that's really cool. So what we've done with the choice of the Lorentz gauge is to basically separate our single second order differential equation into two second order differential equations. But the nice thing is that each differential equation only depends on one function. So you get the second order differential equation that's operating now on A, and you're in the second order differential equation which is now operating on V. And so what I can do is I can try and simplify it a little bit more, but basically hide a bunch of stuff, is if I introduce what's called the D'Alembertian, which is kind of like another version of the Laplacian, is it's now a square, squared. So instead of using the del, I'm using a square, and I have del squared minus mu 0 epsilon naught, the second order with respect to time, or I could write that as del squared minus 1 over the speed of light squared. So essentially I have an operator which basically encapsulates all of the wave function part. So then I now rewrite my equations as a second order differential equation with respect to A, and my second order differential equation, which is operating now on V. And now these two equations are so small that you could write them down and put them in your pocket. Take them anywhere you want. So, so now we've done the separation of potentials. And then the nice thing is, even nicer thing is that we now have a second order differential equation for V, which is now the source of that is the electric charge. And we have a second order differential equation in A, which its source is the electric current. And so it's, there's so much kind of symmetry and simplicity in these two equations that you can't ignore it. It's just something to behold. And so, like I said, the advantages of this are that you now have two separable equations. And if you notice in the definition of the de Lambertian, that I've now combined the space part and the time part basically into one differential equation. So basically, space, del squared, and time are now kind of combined. They're on equal footing. We can treat them now, instead of having a space part, a time part, the separate pieces, we can combine them all into something called space-time. And so this makes it compatible with special relativity. So that's key. So now we've rewritten our Maxwell's equations in terms of potentials. We've rewritten our differential equation of potentials with the Lorentz gauge in a form which will now fit into Einstein's special relativity. The only hang-up now is the fact that we now have to deal with inhomogeneous second-order differential equations because there is a source term. There is an electric charge density, there's electric current density, and so you now are going to have to, the hard part of this whole problem now is trying to solve those second order differential equations. The good news is that you've all been required to take an entire course on differential equations. For this course, we're going to try and go easy on you and choose a rho and a j such that it's not going to drive you crazy trying to solve those second order differential equations. So that's the next step, is to kind of go through examples which are good choices of rho and j that can be solved, and so you can appreciate what a great thing the Lorentz gauge is.